Hello and welcome to my training channel called Training Made Clear. Today's lesson is on industrial communication protocols, part 1 of 8. Before we continue with the lesson, just to help you find all my other training videos, type in Training Made Clear into the YouTube search bar. For my fun channel, type in Percy's Discoveries. Industrial Communication Protocols. This series of 8 courses will cover the following courses. Course 1. TCP-IP Communications, Industrial Ethernet and Yokogawa Brain Protocol. Course 2. Introduction to Industrial Communication Protocols. Course 3. HART Protocol. Course 4. Foundation Fieldbus. Course 5. Profibus. Course 6. Testing and Troubleshooting. Course 7. Yokogawa Brain Protocol. Course 8. Modbus Gateway and NFN. This module covers part 1 of 8 parts. Course 1. Communication Protocols. TCP-IP Communications, Industrial Ethernet, and Yokogawa Brain Protocol. Learning objectives. After completing this module, the student will be able to explain what a communication protocol is, explain why protocols are necessary, describe TCP-IP, describe Industrial Ethernet, explain how messages are formed, explain bits, bytes, and packets, compare Industrial Ethernet with older industrial protocols, explain the Yokogawa Brain Protocol, understand basic testing methods, identify where each protocol is used. Module 1. What is a communication protocol? Imagine two people trying to talk. If one speaks English and the other only Japanese, communication fails. If both speak English, communication succeeds. Computers are exactly the same. Before two devices communicate, they must agree on language, speed, timing, error checking, addressing, and message format. This agreed language is called a communication protocol. Think of it as the rules of electronic conversation. As you can see, there are many various networking protocols. Everyday example. Telephone conversation. Person A, hello John. Person B, hello Peter. Person A, how are you today? Person B, I'm fine. Person A, goodbye. Every conversation has a beginning, a conversation, and an ending. Computers do exactly the same thing. Module 2. How computers talk. Every message contains several sections. A start. Who am I? Who am I talking to? What type of message? The information. Then error checking. And then the end. Exactly like mailing a letter. First you need the envelope. Then you need an address. You also need a letter. You also need to sign the letter. And then you finally need a stamp. Example message. Start. Source address PLC 01. Destination address flow transmitter 07. Command. Read pressure. Data 12.45 bar. Checksum. End. Every industrial protocol follows this basic idea. Module 3. Bits, bytes, and words. A bit is the smallest unit of information. It can only be a 0 or a 1. Think of off equals 0 and on equals 1. A byte. A byte is 8 bits. Example 01001010. 1 byte can represent a number, a letter, or part of a picture. Word. Most PLCs use 16 bits or 2 bytes or 1 word. There's the number 2 bytes. Modern PLCs also use 32-bit and 64-bit words. Example. Temperature 82 degrees Celsius. That's what's stored inside of a PLC, is all those zeros, then 0, 1, 0, 1, 00, 1, 0. To us, 82, to the computer, a binary number. How does temperature 82 degrees C become 8 zeros, 0, 1, 0, 1, 00, 1, 0, stored inside a PLC? To us, 82, but binary to computer. If you see that drawing there of a wave with a number underneath of it, this number is what is shown on a digital over analog picture. The next slide will show what this binary number actually is in decimal. Once I saw a sign that said the following: there are 10 kinds of people, those who understand binary and those who don't. If that sign makes sense to you, then you understand that 10 in binary is the number 2. The next slide will teach you how to read binary numbers and convert them to digital values. From the previous slide, the number 100110110 looks like a binary number. To calculate the decimal value, it is done as follows. We only look at the numbers with ones. So 100110110. We're only looking at the green ones, which is the ones. So underneath each one, starting on the right, you write 2 to the power 0. The next number on the left is 2 to the power 1, 2 to the power 2, and so you move all the way to 2 to the power 8. Calculating, 2 to the power 0 is equal 1. 2 to the power 1 equals 2. 2 to the power 2 equals 2 times 2, which is 4. 2 to the power 4 is 2 times 2 times 2 times 2, which is 16. And then 2 to the power 5 is 2 multiplied by itself 5 times, and then we see 2 to the power 8 is 2 multiplied by itself 8 times. The green numbers are the values. If you add all those green values, you'll get 310. So this is the decimal value for a binary number 100110110. To check the decimal number 310 for its binary value, you can do this as follows. Take the 310 and divide it by 2 equals 155, remainder 0. 155 divided by 2 equals 77, remainder 1. 77 divided by 2 equals 38, remainder 1. 38 divided by 2 equals 19, remainder 0. 19 divided by 2 equals 9, remainder 1. 9 divided by 2 equals 4, remainder 1. 4 divided by 2 equals 2, remainder 0. 2 divided by 2 equals 1, remainder 0. 1 divided by 2 equals 0, remainder 1. Write down all the remainder numbers starting at the bottom to the top, and you will have the binary equivalent for a decimal of 310. So looking at from the bottom, you get 100110110. Now you can understand the previous sign where 10 means 2 and how that number can mean 82 degrees C. Module 4. What is a packet? Computers don't send long messages. They divide it into packets. Think of sending a book. Instead of mailing 500 pages, you mail 50 envelopes, and in each envelope it contains page number, address, contents, exactly how the internet works. That is exactly how it works. Example, packet number 1, header, data, checksum. Packet number 2, header, data, checksum. Packet number 3, header, data, checksum. Module 5. TCP-IP. TCP-IP stands for Transmission Control Protocol, Internet Protocol. It is a language used by the Internet, Ethernet, Wi-Fi, Industrial Ethernet. Almost every modern PLC uses TCP-IP. What is TCP-IP? It's the language of the Internet. TCP-IP is a set of rules that lets computers talk to each other across networks. TCP makes sure every bit of data arrives safely and in the correct order. IP handles where that data needs to go, whether you're sending an email or loading a website. TCP/IP is working behind the scenes. What is IP address? If you look at that big black number, that is an IP address, and above it you can see the red numbers with red arrow pointing to it. That is the binary value of each of those numbers in the IP address. IP is Internet Protocol. IP handles the addressing and routing of data to reach the right device. IP is like your home address. Every device receives an address. Example, 192.168.1.20. Without an address, nobody knows where to send the information. There you can see a conveyor belt with packages on it, and number 32 has fallen off. TCP ensures nothing gets lost. Imagine sending 100 packets. TCP checks, did packet 32 arrive? If not, send it again. This makes TCP extremely reliable. Module 6. Ethernet. Ethernet is simply the road. TCP/IP is the traffic rules. So look at all the yellow ones, Ethernet, and the green ones, TCP-IP. Ethernet cables carry information. TCP-IP tells the information where to go. Typical Ethernet cable, Cat5e, Cat6, Cat6a, and RJ45 connector. Maximum length is 100 meters. Module 7. Industrial Ethernet. Industrial Ethernet is normal Ethernet made tougher. It's designed for dust, heat, oil, electrical noise, vibration, uses industrial switches, shielded cables, redundancy networks, and foster recovery. Industrial Ethernet examples: Profinet, Ethernet IP, Ethernet Cat, Modbus TCP, PowerLink. These are industrial protocols built on Ethernet. They add rules for real-time control, device discovery, diagnostics, and synchronization. Module 8. Industrial Protocol Comparison. If you look at the protocol, then speed, distance, advantages, and disadvantages. HART, speed 1200 bit per second. Distance 1500 meters. Advantages, very reliable. Disadvantages, slow. Then look at the brain under speed, distance, and advantages and disadvantages. Then Modbus. Then Foundation Fieldbus H1, then Ethernet, and then gigabit Ethernet, and then fiber internet. Look how fast that is, 1 to 100 gigabits per second, and you can do many kilometers depending on the fiber, immune to electrical noise, all good things. Module 9, Advantages of TCP-IP. It's extremely reliable, it has a worldwide standard. It's easy to expand, easy troubleshooting, supports thousands of devices, it's fast and works with the internet. Disadvantages are, it's got a large overhead, it's more complicated, it needs IP addresses, it can be affected by cyber attacks, it requires network management. TCP Transmission Control Protocol is considered reliable because it guarantees that the data is delivered to the recipient complete, uncorrupted, and in the exact order it was sent. Even over an inherently unstable internet, the protocol achieves this through 5 core mechanisms built into its architecture. 1. Connection-oriented setup. Before any data is exchanged, TCP establishes a verified connection between the sender and the receiver. 3-way handshake. The device exchanges SYN, synchronize, and ACK, acknowledge, packets to agree on connection parameters and synchronize sequence numbers. Guaranteed path. This ensures both endpoints are active and ready to process data before transmission begins. Number 2, sequence numbers, ordering. IP networks route packets individually, meaning they can arrive out of order. Packet labeling. TCP assigns a unique sequence number to every single byte of data sent. Reassembly. The receiver uses these numbers to sort the packets back into the correct order and seamlessly discard duplicate packets. Number 3, acknowledgements and retransmissions. No lost data. TCP leaves no packet behind by tracking where the data actually arrives. Positive acknowledgement. The receiver sends back an ACK package to confirm exactly which bytes it successfully received. Retransmission timeout, RTO. The sender sets a timer for every packet. If an ACK is not received before the timer expires, the sender assumes the packet was lost and automatically resends it. Number 4, error checking, checksums. TCP ensures that the data received is exactly what was sent, without corruption. The checksum test. Every TCP header includes a mathematical value based on the packet's contents. Discarding errors. The receiver recalculates this value. If the numbers do not match, the packet is flagged as corrupted, thrown away and triggered for retransmission. Number 5, flow and congestion control. TCP monitors network health to prevent drop-in packets due to overloaded systems. Flow control sliding window. The receiver constantly tells the sender how much buffer memory it has left. The sender limits the data transmission to match this budget, preventing the receiver from being overwhelmed. Congestion control. If the network paths become choked with traffic, TCP automatically slows down its own transmission rate using algorithms like slow start to prevent all network collapse. Checksums and error checking. Flow and congestion control. Module 10. Open Systems Interconnection. OSI Model Simple View. Operator screen, application, TCP-IP Ethernet cable. Each layer performs one specific task. This is simple view. The right-hand side would be a more detailed view. Module 11. How messages are checked. Every packet contains checksum, CRC, sequence number, address. If one bit changes, the receiver says, "I found an error." Sender sends the packet again, TCP, or discards it, some other protocols. Module 12. Testing TCP-IP networks. Technicians use ping. Ping 192.168.1.50 checks. Can I reach this device? Traceroute. Shows every network step. Network analyzer. Example. Wireshark. Shows every packet traveling through the network, including headers, addresses, ports, and payload. Cable tester. Checks. Opens, shorts, crossed wires, shield faults. Industrial network testers. Measure packet loss, jitter, noise, speed, cable quality. Module 13. Industrial Ethernet applications. Used in PLC, remote I/O, HMI, variable speed drives, analyzers, SCADA, control room. Entire plants can communicate over one network. Module 14. Yokogawa Brain Control Protocol. What is BRAIN? Yokogawa Brain Protocol. BRAIN stands for Bidirectional Remote Advanced Instrument Network. It was developed by Yokogawa in the 1980s as a proprietary digital communication protocol for smart field instruments. Unlike HART, which superimposes digital communication on a 4 to 20 milliamp signal using Bell 202 FSK tones, BRAIN uses a different digital modulation method over the same two wires carrying the analog signal. Where is it used? Yokogawa. Pressure transmitters, temperature transmitters, flow transmitters, level transmitters, positioners, older DCS systems. It was widely used before HART became the dominant vendor, independent protocol. Wiring, only two wires, 24 volt DC positive to transmitter, negative to 4 to 20 milliamp, plus digital communication. The digital signal rides on the same loop without interrupting the analog measurement. What does it look like? To the eye, nothing unusual. Just two wires, 24 volt DC, 4 to 20 milliamp. The digital communication is invisible. BRAIN communicator. Yes, you need one. A BRAIN-compatible communicator or Yokogawa handheld terminal is normally required to access configuration and diagnostic information. Modern asset management software and some multifunction communicators can also support BRAIN if they include the appropriate software and device descriptions. With it, you can read pressure, read diagnostics, change ranges, calibrate, configure damping, check sensor status, and so on. As a comparison, testing BRAIN. Use digital communicator. Loop calibrator when applicable. 24 volt supply. Multimeter. Oscilloscope advanced troubleshooting. You verify. Loop current. Device response. Digital communication and configuration and calibration. Now you can compare feature with BRAIN and HART. The company, Yokogawa, HART is multi-vendor standard. The loop, both are 4 to 20. Digital data, both are yes. Configuration, both are yes. Diagnostics, both are yes. Widely supported, mainly Yokogawa for BRAIN and most manufacturers for HART. Special communicator, usually BRAIN compatible for BRAIN and HART compatible for HART. Summary. A communicator protocol is a set of agreed rules that allows devices to exchange information correctly. Messages are organized into packets containing headers, addresses, and control information, data, the body, and error checking fields. This is conceptually similar to saying hello, exchanging information, and saying goodbye, although real protocols use binary fields rather than literal words. TCP-IP provides reliable addressing, routing, and delivery of information. Industrial Ethernet is Ethernet used with industrial communication protocols such as Profinet, Ethernet IP, Ethernet CAT, and Modbus TCP for factory automation. Data is represented as bits, grouped into bytes, and often processed as words inside PLCs and controllers. Error detection used in checksums or CRC helps ensure data integrity. Networks are commonly tested with tools such as ping, cable testers, protocol analyzers, example Wireshark, and industrial network analyzers. Yokogawa Brain is a proprietary digital protocol for smart field instruments that communicates over the same two wires as the 4 to 20 milliamp signal and typically requires brain-compatible communication tools for configuration and diagnostics.